I hope everybody can see the screen.
Yeah, screen is visible.
Yeah, great. Okay. So reinforcement learning is a type of machine learning, which is one of three main. That is supervised learning, unsupervised learning, and reinforcement learning. So in supervised learning, I'll give you a brief on all of them. In supervised learning, we are going to give our code or our bot a data set, and we're going to tell it, say it's a data set of cats and dogs. Then we're going to show it every picture and tell it that this is a dog or this is a cat. So eventually your robot is going to learn how to classify on its own. In unsupervised learning, you're going to give it the same data set, but you're not going to tell it whether or not it is a dog or a cat. It's going to be unlabeled. So here the bot is going to learn on its own whether or not what it's looking at is a dog or a cat. It will have to classify based on features, etc. Reinforcement learning, however, is very different from both these types of learning, wherein your bot is going to learn from experience. Reinforcement learning may you're gonna give your bot a reward, positive or negative, based on whatever actions it takes and what you want it to be doing. So these are some applications of reinforcement learning. I'll go through those first before we actually learn about what it is. So of course, one of the most interesting applications of reinforcement learning is that is self-driving cars, wherein your car learns on its own whether or not to brake, whether or not to turn or not, based on what has happened before and what the traffic conditions are. Then there is industry automation, wherein you take data from data centers, you predict how often
Misty,
combinations will affect various things, and based on that you automate your
Misty,
anything in the industry.
Misty, your slides are not changing. Can you please put them on the slideshow?
Yeah, I'll try. I'll see what's wrong. I'll just stop sharing for a second. Okay, how about now?
Yes, yes. Continue.
Okay, so then after industry automation, you have trading and finance. So your models can be used to predict future sales as well as stock prices, etc., which is incredibly useful because a stock market is a very quick changing entity. So if you have a machine doing it for you, it's obviously going to be faster than a human. Then there's NLP, which is natural language processing. So so basically over here, you are changing you're translating from one language to the other. There's text summarization, question answering, machine translation, and so much more. So over here you are using reinforcement learning in order to learn quicker. Then of course there's healthcare, where patients can receive treatment based on policies learned from RL systems. So it is able to find optimal policies using previous experiences without need for previous information on the systems and all. Then you have recommendation systems, which goes a long way. It ranges from what you're buying, like Amazon, Netflix, so what you're watching, what you're buying, like on say Myntra, and even what you're looking at in Google search. All of those are recommendation systems based on RL. That is why every search you make is personalized to your tastes. So eventually your machine learns that when this person is logged in, this is what the person's interests are. Then there is marketing and advertising. Over here, again, based on what a what a market's response is based on an ad or some product, your machine is going to learn whether or not this product is wanted or not. And then you have image processing. So here you capture the image and you analyze and manipulate it. And here ML models are used to simplify the image trends, etc. So this is one of a very interesting example of reinforcement learning, wherein there is a robotic dog, which after taking reference, which is a form of supervised learning, is going to learn how to walk. So here the negative reinforcement is when it falls. So eventually it learns that if I walk like this, I'm going to fall. But if I walk like that, I'm not, which is positive reinforcement. This is very similar, I guess, in real life also to how we learn, which is again reinforcement learning. When a baby learns to walk, your baby is going to fall down first, and when it falls down, it's hurt, which is negative reinforcement. But when it walks nicely, your parents are going to encourage you, which is positive reinforcement. So in everything we do, in everything we learn, there is reinforcement learning. From say not touching a flame, negative reinforcement, to studying for a test, which is positive reinforcement. Everything we do these days is based of reinforcement learning. So the principle here is that it's a computational approach to learning from interaction. We learn from interaction non-computationally, obviously. This is computational. So it is goal directed, and the idea is that you map situations to actions. So if you make an action, you're gonna get a reward signal, which is numerical. If it's higher, it's good. If it's lower, then you're aiming for a higher reward signal. So, so it is based off trial and error, and the principle of delayed award. So your bot is on S9 over here. Say it goes to S10. We want to reach this diamond. It's gonna try to go to S6 and it's gonna return because it's not possible. Then it's gonna go to S11, and then if it goes to S12, its reward is going to be -1. That is delayed reward. So your bot is not going to go there on S12 at all because you don't want to go to S8. Then it can go from here to here or here to here. But the idea of delayed reward and trial and error is your bot is going to learn slowly, and based on the rewards it will get after say 8 or 10 moves. These are some of the jargon used. It's very important to know this because we'll be using it again and again in this session. So the first term is agent, which is the entity which is in the environment and which is doing all the actions. That is the agent, I repeat. Then, of course, you have the environment, which is very, very important in reinforcement learning, which is the area where your agent is. This is where your agent is going to do all of its actions. The environment is what your agent is going to be reacting to and what it is going to be acting in. Then you have actions, which is any move taken by the agent within the environment. These are all anything that your agent does at all. It moves forward, backward, it shuts off, it turns on, anything at all. Then there is the state, which is a situation returned by the environment after each action is taken. So anything you do is going to have a reaction. Similarly, anything an agent does is going to have a reaction in the environment, be it a numerical reward, be it a changing of the environment, anything at all, which is the state of the environment. Then there is a reward, which is the feedback given from the environment, which is basically a numerical reward, which is either positive or negative, which is positive reinforcement, negative reinforcement. And this is the whole thing, that is what we are based off. And there is policy, which is the strategy applied by the agent for the next action. So if you're in maze, then the strategy would be to say turn left or turn right to avoid a blockage or something. That would be a policy for the agent. So the policy is always to get maximum numerical reward in minimal time. And this is the process, which is basically what I just explained. Your agent is going to perform an action on the environment, and the environment is going to return a reward and a state, based on which your agent is going to perform the next action. Okay, now agents and environments are very important in reinforcement learning. We must remember that while an agent is interacting with the environment, the agent cannot change the rules of the environment. For example, us humans, if we are an agent and the earth is an environment, we cannot change the rules of the earth. We cannot change gravity. We cannot change that plants give out oxygen. We cannot change any of that. What we can do is interact with the earth and get rewards or states from it. So if there is deforestation going on, that is you interacting with the earth. You're not changing any of the rules. You're just cutting down trees. And that is going to give you a negative reinforcement in the form of global warming, which is, again, you're not changing any of the rules, you're just getting a reaction back, that is negative reaction. Or say you clean up a beach and fish come to the sea, or you get more diversity in plant life, then that is positive reinforcement. So environment is very important and it can be categorized in many ways. Um, so you have a discrete or a continuous environment. In a discrete action space, you can take very discrete actions only. You go up or down. You cannot go somewhere in the middle. You go left or right. You cannot go say southwest or somewhere in the middle of that. No angles are allowed. Similarly, your speed will be 1, 2, or 3. You cannot go at 1.2 or 2.2. Continuous, however, you can move at angles. You can have various speeds, and that's the basic idea over here. So then you have deterministic or stochastic. In a deterministic environment, the next state of the environment can always be determined based on your current state and the agent's actions. In stochastic, however, you can never determine the next step. Say you are in a car, and if you turn your steering wheel left, there's a 100% chance of you going left. So that is deterministic. But if your steering wheel is broken, say there is a 70% chance of you going left, but a 30% chance of you going right, then that is stochastic. You do not know for sure what is going to happen. Then you have a single agent environment and a multiple agent environment. In a single agent environment, there's only one agent that exists and interacts with the environment. Multiple agents, there are multiple agents. That's a pretty self-explanatory term. Then you have episodic and sequential environments. In an episodic environment, the agent's actions are confined to the particular episode only. Say you're playing a game of cups. There is one ball beneath one of 3 cups. You shuffle them and you find the ball or not. That is one episode. Whether or not you find your ball right now is not going to determine whether you're going to find the ball next time, or whether or not you found it the previous time. However, in a sequential environment, it doesn't work that way. If you take an action now, it is going to impact all of your future actions. Like, say, a game of chess, a move that you made at the second or the third turn may impact the outcome of your game, which is of, say, 100 turns. You, of course, have a fully observable or a partially observable environment, wherein you can either see the entire environment, again, like a chessboard, or you can see only some of the environment, which is like, say, a game of Subway Surfers, where you don't know what's coming next because that's only some of the environment. Then you have, okay, so that's the basics of agents and environments. Why don't we have the people tell us what kind of an environment this is? So anybody who has the answer can please raise your hand, whether it's determinist, whether it is discrete or continuous first. Does anybody have an answer? Okay, so this would be a discrete environment. Then as you can see, your Pac-Man can go only left, right, front, or back. There's not, and the speed doesn't change either. Then it is whether it is a stochastic environment or a deterministic environment. So this would be stochastic because it is continuously changing. Then whether this is single agent or multiple agent. Now this is a single agent environment simply because the only person who's the agent here is the Pac-Man. The ghosts are a part of the environment. You cannot change their rules or anything. Then this is sequential. What you're doing now can affect your actions later on. And it is fully observable. You can see your entire game. Okay, so that's it for me. Are there any doubts? All right, then if there are no doubts here, then I will hand over to my friend Alekya, who's going to take, no, I'm going to hand over to my friend Jiya, who's going to take the session from here.
Thank you, Mishtee. Hello, everyone. Let me share my screen. Okay. I hope you are able to see the slideshow.
Yeah,
Okay.
Jiya, go on.
So, my name is Jiya Bhagat. I'm one of the AI promoters at SMLRA, and I'm going to talk about one of the very important decision-making processes in reinforcement learning, that is Markov decision process. Uh, Before diving deep into MDP, let's understand what it is exactly. So, as you are familiar with the terms, it is a discrete time stochastic control process. MDP is a discrete time stochastic control process, which says that based on the probability, we can find an optimal code or an optimal way for all the state transitions using an agent. I repeat, based on the probability, our Markov decision making process can find an optimal route for all the state transitions using an agent. We all know that in reinforcement learning, we have states, we have probabilities, we can make decisions using an agent. So in reinforcement learning, we use Markov decision process. So here, MDP deals with five important tuples of five main essential elements. S stands for state, A is the action, capital T denotes a transition probability matrix, capital R denotes a superset for all the rewards denoted by small r, and gamma is a factor that you will come across while we see the main equations for MDP. So let's move on to the first. First is an agent. Agent is that object, it's that process or algorithm which completes the task while being bounded by certain set of rules or policies. So agent is that object which completes the task, which performs the actions denoted by A, which performs the action while being bounded by certain set of rules or policies. So what is action? Action is anything that is to complete the task. The agent will do some activities, right? The agent will perform some actions while remaining within the boundaries of its policies. So action comes as the second essential element in MDP. State, with the help of these actions, the agent can make a transition. The agent can move from one state to another. Next is rewards. Okay, so reinforcement learning has got rewards to play a very important role. If you progress towards an optimal route, or if the decision made in that particular situation is correct, then your agent has to be rewarded. Else, the agent is penalized. The algorithm is designed in such a way that the agent or the model gets trained based on the rewards or penalties it receives for its particular actions. That is the whole idea behind reinforcement learning. The agent gets trained based on the rewards or penalties it receives for its actions or activities. Last is environment. Environment denotes, as the name suggests, environment is a surrounding in which the agent works. It denotes the transition dynamics inside which the agent performs its actions. The agent moves from one state to another, and along the way, the agent also receives rewards or get penalties. And everything happens based on the probability. Everything happens only on the basis of probability. Okay, so let's understand this whole concept using an example. Okay, so the example is about consider a robot who is kept on a plain flat surface. The robot is kept on a plain flat surface, and its task is to collect all the cans which is kept randomly anywhere on that surface. So the robot is standing on a surface, and there are n number of cans which are placed randomly anywhere on that surface where the robot is standing. Here, the robot is our agent, and he will perform actions to collect the can. So if you think carefully, we will have three main actions for the robot to perform. First will be seek of can, that is searching for the can. Obviously, for collecting the can, he has to search for it, right? So that is denoted by A1. It's comma here, but it is subscript 1, A1, action 1. The robot will try to find where the can is, how far the cans are present on that surface, and hence the action 1. The second action is to perform collection of the can. After searching for the can, the robot has to collect the can, hence it is denoted by action 2 or A2. The third task can be charging itself. Let's assume that the robot is battery powered and it will lose its charge while it functions or performs the other actions. So the third important action becomes plug in for charge, that is A3 or action 3. Throughout this scenario, you will see that the robot will make a transition, or the robot will be in two particular states. One, when the robot's battery is running low, that is low state or L. And the other is when the robot's battery is sufficiently charged, that is the robot is in high state or H. As the robot performs these actions, we will observe that the robot or our agent, the robot is our agent here, right? So our agent will go from high state to low state as its battery keeps on dying. But whatever the state is, our concern is that the robot should be able to complete its task of collecting all the cans in a most effective manner. That is our objective, that is our aim to accomplish. So, so apart from actions and state, in this example, we will take along one more important concept, that is rewards. We are saying that our objective of the robot is to collect the cans. So, as the robot collects the can, we will have to reward him. Hence, the reward would be +1. Similarly, if the robot collects no can and spends all the time in searching for it, then its battery will constantly decrease. Hence, we will penalize him by -3 or negative reward. We call this as a negative reward. All these three concepts, state, action, and reward, together they form a policy. We call it as a policy of machine and denote it by pi. But note, policy of machine is not complete without a state transition matrix or state transition matrix in terms of probability. What is that? In a simple language, I can say it is basically a matrix. It is a grid where each grid point denotes the probability of any movement to occur while changing from one state to another via performing a specific action. I repeat, each grid point denotes any probability of robot moving from one state to another via performing a specific action. We'll understand. Let's understand this flow of action, how transition in states occur, how rewards are being given via this example of robot and can. I have not made the transition matrix here, but we'll first understand the flow diagram. Okay, so this is going to be quite long. We will have to see many scenarios. So please stay with me. Let us assume initially the robot is in L state, that is low state, and our robot is performing task A1, action 1, that is seeking for the can, searching for the can. So here our agent is performing a search for the can. While the robot searches for the can, its battery is constantly draining out, as well as the objective is not being complete. Our objective is to collect the can. So while he is searching for the can, our objective is not being complete. On the top of that, our battery is also decreasing constantly. Hence, we have penalized him here by 3 points. Now, if the robot is performing, say, task A3, that is plugging in for charge. Since it is in low state already, it is required for him to get charge to work further, to function further, right? So we haven't penalized him here. But since there has been no gain, there has been no completion of our objective. That is, there has been no collection of can. We haven't rewarded him as well. So 0 points or no point has been given to the agent or our robot. And the third possible situation in the low state can be the robot finds the can and the robot is collecting the can. That is, the robot is performing action 3 or A2. Since he is collecting the can, he is completing the objective. Hence, we have rewarded him by 1 point. Hence, +1 here. Okay, if you observe in all the above situations, there has been loop created. These orange, white, and green loops, they actually denote that there has been no change in the state. The robot starts from the low state and continues to remain in the same state while performing these 3 actions. But state transition is quite possible, huh? State transition is quite possible while taking these actions. So suppose the robot is performing say action A3, that is plugging in for charge. When the robot has been plugged in for charge, its battery will increase. Its battery level will increase slowly. Its battery level will increase and increase so much so that it will exceed a particular threshold value, and the robot will make a transition from low state to high state. He will move from low state to high state as its battery gets sufficiently charged. So you can see that while performing task A3, there are 2 possibilities. Either the robot continues to be in low state, as in this case, or the robot makes a transition to high state, as in this case. So if you see here, there has been no point given to him. Neither the robot has been rewarded because there has been no fulfillment of our objective, nor it has been penalized because it has brought the robot from low state to high state. Now, when you have come to the high state, when the robot is in high state, the robot again starts searching for the can. Obviously, before collecting the can, the robot has to search for the can, right? So he performs action A1. Now, if you see this loop, you'll understand that while searching for the can, the robot continues to stay in the high state. Why is that so? Because obviously, after performing just one single action, the robot's battery will not die out suddenly, right? So there has been no penalty given to him. Unlike here in the low state, where he was penalized by 3 points. Now, when the searching action is over, the robot finds the can, he will collect the can, right? Hence, A2 action will be performed. He will complete the objective, and then he will be rewarded by 1 point for completing the objective. Okay. Now, if you see here, there has been no arrow. There has been no orange arrow coming from high state and going to high state like here. There has been no action undertaken for plugging for charge for performing action A3. Why is that so? If you have guessed, you might have guessed right. Like the reason would be since the battery is already pretty much high, since the robot is in high state, there is actually no need for plugging in for charge. Hence, A3 action has not been performed. As the robot starts searching for the can again, after collecting the can, he again starts searching for the can. It is very much possible that this time his battery will start to drain out, and it is possible that during the search action being undertaken, its state changes from high and he returns back to low state. So here we have penalized him by -3 because he neither collected the can, he neither fulfilled the objective, and on the top of that, he brought the battery from high state to low state. So the robot had to get penalized. Along the same lines, if the robot performs the task, say A2, okay, and while performing this task A2, that is while collecting the can, the robot goes from high state to low state, you can see that we have not penalized him. Instead, we have rewarded him. That is because he has completed an objective even though he brought the battery from low to high. So Like this, you can make transition from low state to high state, and you can make decisions in every possible scenario. So, okay, so this was the entire example demonstrating the transition from one state to another, how the agent gets rewarded or penalized, how the agent undertakes certain actions. Let's look at how the total rewards are calculated. Look, we'll see these actions from rewards point of view. Okay. Initially, the robot is in low state as it was in the earlier example, and the next state would be high. So first, since the robot was in low state, he will perform the action to charge first. He will perform action A3, and since there has been no completion of the objective, there has been no can collected, the reward here is 0. So the net reward at this stage becomes 0. Next, he performs action A1, that is seek of can, searching for the can. He searches for the can, he decreases the battery's level and comes back to low state, and therefore he is penalized by 3 points. So as you can see, the net reward calculated here becomes -3. Similarly, he performs action A3. He plugs himself for charge. He goes from low state to high state, and hence no penalty has been given to him. So the total reward continues to be -3 at this stage as well. Next, after coming to the high state, he will first search for the can before collecting the can, right? So action 3 has been performed. But here you can see that there has been no penalty given, unlike in this case, right? I have explained the reason before. That is, the battery level remains the same. Battery level remains at the high state, hence he has not been penalized. And therefore the reward becomes -3 as it was before. And last, after searching for the can, he collects the can, he finds the can and he collects the can, so he is rewarded by 1 point, and then the total reward becomes -2. So in this entire process of calculating the total reward, you will observe that the total reward in the end, which is -2 here, is highly dependent on the sequence in which the actions have been performed. If I had changed the sequence, if I had changed the initial situations, if I would have said that robot is in high state, he performs A1 action or A2 action first, the net reward that comes in the end would have been different. So that is one important property. The other important property of probability, properties of probability which comes into picture. The probabilities, it says that the probabilities of all the actions to be performed at a particular stage always sum up to 1. I repeat, the probabilities of all the actions, that is A1, A3, A2, etc., that is to be performed at a particular state, let's say low, always sum up to 1. For example, let's say the robot is in low state and the probability of performing action A1 is, let's say 0.6. So we can be sure that the probability of performing action A3 at low state would be 1 minus 0.6, which is 0.4. So this is the entire concept of Markov decision process. At this final stage, let's look at the main equations. Let's encounter the gamma, which I had talked about before in my introduction. So in this, we have two equations. First is a probability equation, where S denotes the current state where the robot is present, where the robot is standing presently. S dash is the next state where the robot will make a transition from, and A is action. So this probability says that it is the probability of transiting from current state S to next state S dash via performing action A. Hence the name state probability or state transition probability. So the equation says that this probability is equal to the summation of all the probabilities of rewards received in every possible scenarios. The reward received could be positive or negative, but the equation says that the probability of receiving reward by an agent is when it is summed up to, when it is all added together, it will give us the value of state transition probability. So here it says that the reward received by the agent, R denotes the reward received by the agent from for making a transition from current state S to next state S dash via performing action A. The reward and here R denotes the reward received at particular state transition, which lies under the superset called R, capital R. Okay. So this is a probability equation. To calculate this equation, we use a generative equation. What is generative equation? In simple language, I can say that generative equation calculates all rewards. I repeat, a generative equation calculates all the rewards received by the agent. This equation means that, let's say at particular time t, the reward received by the agent to make a transition from current state to next state is R t plus 1. That is the reward received in the next time interval, in the consecutively next time interval. Similarly, the reward received by the robot for making a transition from next state to next state would be R t plus 2, and hence RP3 plus 3, RT plus 4, and so on. So suppose you have to calculate the total rewards received in n time intervals, in n time span. Now what would you do? In Markov decision process, you will use this generative equation, which would calculate the reward received in n time intervals, that is RT plus 1, RT plus 2, RT plus 3, and so on till RT plus n. But what about this gamma? What is this gamma, and why is its power increasing consecutively? So there is a concept in MDP. We want our agent to find optimal paths. We want our agent to make optimal decisions. But if you have a model that goes through an infinite number of states, then how long will your algorithm will recalculate the total rewards? So here, we have already assumed that the reward for transiting from every current state to every next state would be RT plus 1, RT plus 2, and so on. But here, when you are calculating the next reward, you will also consider a multiplier. You will also consider gamma, which is, as you can read, it's a discount factor. Now, what is this? Why it is being used here? So a discount factor, as you can read, its value ranges from 0 to 1. So discount factor will always be a positive fraction, and it will always be defined by the user. So as its power increases consecutively, its value successively diminishes. We all know that when we raise a fraction to some power, its value decreases. So as the power increases consecutively, the value of gamma successively diminishes, and hence the value successively diminishes the value of reward as well, which is being multiplied, and hence the whole product, the value of whole product finally or eventually tend to 0. I repeat, when the gamma or the discount factor is being raised to some power and multiplied by reward, eventually at some point of time the product will tend to 0. The power of discount factor increases, the value of reward at that particular state will decrease, and there will be a saturation point after which the value of all further rewards will remain the same, that is 0. This is called as convergence. We are actually converting, or we are actually converting an infinite situation to a situation which will give a finite value. So Okay, so this was the entire concept of Markov decision process. If you have any question, feel free to ask. Okay, so there can be one obvious question that will the value of discount factor remain constant or will it increase or decrease with the state? So the answer is in fact that the gamma's value or the discount factor's value is independent of the state. It does not depend upon from which state to which state the agent is moving. And it is defined by the user. It is user defined value. The algorithm, the person who is writing the algorithm will decide the value of gamma or the value of discount factor for his model. Yeah, so that was it from my side.
Just a second here.
Yeah.
There were questions in chat. First, so can I take the questions first?
Yeah, please.
So first question was why rewards and penalties are not 1 and -1. So it totally depends on the situation, like the state, the action that you're performing, and the environment you are in. Like suppose if you're driving a car, and if I say if you drive correctly, then I will give you one chocolate. Okay, so that is the reward that I'm giving to you. But when you meet accident, I will not say you to give me one chocolate back, correct? Because that can be fatal. So it is totally dependent on the environment and the actions and the states that you are in. So penalty, we always penalize the things that we don't want to happen, so that our machine learning models don't run wrong things. Basically, if you see, if the example that was taken, the robot example, if as there are many cans there, cans are basically litter that the robot has to gather, correct? So if the robot is gathering them correctly, and coming back to its charging point before getting completed discharge, then that is the ideal situation we want, correct? But suppose if he was not able to pick any can and he came to the charging area, then that is the worst case scenario because it lost his battery also, the energy was lost, and nothing and no work was done. So we don't want that. So we'll highly penalize it. So by doing that, the robot will know that that thing is not to be done ahead. Like in the next iterations when he goes to pick the litter, that things must not be done. At least he must pick something, and that thing is learned. So in that way, rewards work. And and one more question was what exactly are rewards? So see, if I speak in theoretical terms, then rewards and penalty are nothing but points that you give or give to the bot, like to any machine learning model. Okay. But when we talk about the coding perspective, then we assign some value, some starting value to reward. Like starting value, reward equal to some starting value. Suppose 0, suppose 100, anything can be assigned. And then we basically give the rules. Like if it does this, add 10 to it, add 10 to the value. If it does in that way, if it goes in wrong direction, then add -10 to that value, -10 to that value. So that is reward and penalty example. I hope it is clear now what reward and penalties are. If you have any doubt, you can raise your hand or you can put in chat. Okay, so as I can't see any hand raised and question in chat, I would like to call Alekya to continue from here.
Hello, I'm Alekya, AI promoter at SMLRA, and I will be discussing about Bellman's equation. So first, let me just share my screen. So is my screen visible?
Yes, Alekya.
Yeah. Okay. So first, these are the contents. First, we'll be looking at the importance of Bellman's equation, and then a few terms that we need to know in order to understand the equation. Those are the discounted reward, P function, and Q function. And then when finally look at the Bellman's equation, where we'll see why is this equation needed, what does it do, and how does it do. And then we look at its derivation, and finally a sample program. So first, let's start with the importance and introduction of Bellman's equation. So what exactly is this equation? So this equation simplifies the computation of a value function. And now I know most of you don't know what is a value function. So in order to understand that, we'll first take a simple example where we won't be using this equation, and then let's see what happens. So this is the environment where the agent is at state 9, and the goal of the agent is to reach state 4. And on doing so, it would get a reward of +1. There's a fire pit at state 8. And if the agent reaches there, it gets a reward of -1. Then state 6 is blocked. That is, the agent cannot cross it over. And all the other states have a reward of 0. So only states S4 and S8 have reward of +1 and -1 respectively. So the agent starts at S9, and by trial and error method, it gets the best path. So the best path would be S9 to S5 to S1 to S2, S3, and then finally S4. And there's one more option also, that is S9 to S10, S11, S7, S3, and then S4. Now, why are these the best path? This is because these are the shortest path that give us the reward +1. So the agent selects one of these. So let's assume the agent selects the first path, that is, it goes up. And then at the end, it gets the reward of +1. So to track its path, it needs to assign some value to its previous state. So it assigns value 1 to each of its previous state. So when the agent is at S4, it assigns value 1 to S3, and then S2, S1, S5, S9. So this is how the value is assigned. But now let's assume that the agent has moved upwards from S9, and the agent is at state 1 now. Now, as you can see, there are two states, 2 and 5, with equal values on both the sides. So this creates a state of confusion for the robot. So he doesn't know go to which direction, like S2 or S5. The same situation arises when the bot is in state 5 or state 2. And hence, this approach of assigning value 1 to each of the previous state is not the correct approach. So here, we will be using Bellman's equation, which will in short calculate the value of a state. And now in order to understand how does the equation do that, we need to first look at 3 terms. And the first one is discounted return. Discounted return is basically the long-term discounted reward. Now, what does long-term mean? Long-term means the total reward that the agent would get over the whole episode. And now, what does discounted reward mean? So, as you know, in an episode, the agent would get numerous rewards. Now, there might be a situation where the future rewards are not as important as the immediate rewards, or the future rewards are equally important as the immediate rewards. So, there's a factor called discount factor which decides this. And then this is the expression for discounted return. And if you take the factor common over here, you can see that, again, this term is nothing but G subscript T plus 1. So finally, this is the expression for discounted return. And then we have the discount factor, which can have values between 0 to 1, both inclusive. And if the value of this factor is closer to 0, then the future values are not as important as the immediate rewards. And if the value of the factor is closer to 1 or equal to 1, then the future rewards are as important as the immediate rewards. So this was the first term that we had to know. Now let's go to the second function, that is the V function. So V function, or the state value function, this basically computes the value of a state. And now what does this value mean? So this value represents how good or bad a particular state is. And now this is the mathematical expression for it. And what does this expression mean? So this expression says that the value of a state by following a policy is equal to the total expected return at time t starting from state S. I'll repeat. This equation says that the value of a state S following a policy is equal to the total expected return at time t starting from state S. Now, as you know, policy is the thought process behind selecting an action. And over here, we are just substituting the expression for discounted return, which we had just seen in the previous slide. So this is the expression for discounted return. And now let us take a look at a few examples so that you are able to understand it in a better manner. So this is a very simple example, and let's assume that the agent starts from state S0. It has two options to go, either state 1 or state 2. Now, if the agent goes to state 1, it gets a reward of 1. And if it goes to state 2, it gets a reward of +2. Now, also let us consider 4 different policies. And in each case, let us calculate the value of the state. So the first policy would be always left. Now, in this situation, in this policy, what would the value of the state be? It would be the probability of taking this action. And the probability of taking an action which is always left is 1, right? That multiplied by the reward that the agent would get by taking that action. And that is 1. So we get the value of the state as 1. Next, the next policy is always right. So in this case, again, the value of taking the action always right is 1. And the reward that the agent would get by doing so is 2. So the value of the state is 2. This is the fourth policy where the agent can take left with a probability of 0.5 or take right with a probability of 0.5. So in this situation, the value of the state would be again the probability, which is 0.5, multiplied by the reward, that is 1, plus the probability again, which is 0.5, multiplied by the reward, which is 2. So the value of the state comes out to be 1.5. With the fourth policy, where thus the probability has changed. So from these 4 policies, you can see that the second policy, that is always right, gives us the highest value of state. And hence, this is considered to be the best policy. And this is how the best policy is chosen. Now, what happens when I tweak this environment a little bit? Now, let's see what happens. So there's a little change over here. In the early example, state 2 was the end state or the termination state. But now, state 2 is no longer the termination state. State 3 is the termination state over here. So the reward system is when the agent goes from state 0 to state 1, it gets a reward of 1. When it goes from state 0 to 2, it gets a reward of +2. And when it goes from state 2 to state 3, it gets a reward of -10. Let us consider the same policies. The first policy was always left. So in this case, nothing changes. But then the second policy, which was always right. In this case, what happens is that the probability of selecting that action remains same. But then the reward over here changes. And that is because when you go from state 0 to state 3, you get a total reward of 2 minus 10, which is -8. So that is how the value of the state changes. Now the third policy, which is to take left with 0.5 probability and to take right with 0.5 probability. In this case, again, the probability is 1, the reward is 1. The probability is 0.5, the reward is 1, plus the probability, which is 0.5, multiplied by the total reward, which is -8. So the value of the state comes out to be -3.5. And this is similarly for the fourth policy. Now over here, you can see that the second policy that is always right is no longer the best policy because that gives us the lowest reward. So in this situation, the first policy that is always left becomes the best policy. And this is how a small change in the states and the reward system affects the process of choosing the best policy. So now we have covered 2 terms, that is the discounted return and V function. Now let's go to the last term, which is the Q function. So just like value function or the V function, Q function tells us the value of taking an action. And this is the mathematical expression for it. And now what does this say? This says that the value of taking an action A from a state S by following a policy is equal to the total expected return at time t starting from state S and by taking an action A. So let me repeat. This equation says that the value of taking an action A from state S by following a policy is equal to the total expected return at time t starting from state S and by taking an action A. So here also we are just substituting the expression for discounted return. And this is the final formula for calculating the Q function. Now we have two functions, that is V function and Q function. So we need to establish a relation between these two. And that relation would lay the foundation for Bellman's equation. So in order to create that relation, we need a term. And that term is probability of selecting an action. So what does this term mean? So this term means that the sum of probabilities of all the possible actions that the agent can take from a state S by following a policy is equal to 1. So let me repeat. This term says that the sum of probabilities of all the possible actions that the agent can take from a state S by following a policy is equal to 1. So using this term, we establish a relation between the Q function and V function. So this is the relation. And this makes sense, right? Because this is what we were doing in the previous examples. We are multiplying the probability and the reward. So we are doing the same thing here. The probability of selecting that action multiplied by the action value function. And that gives us the value of a state. So till now, we have covered all the three important terms that we had to know. So now we can dive into Bellman's equation. So let's start with it. So what exactly does this equation do? So this equation decomposes the value function into two parts, that is immediate reward and discounted future values. So you can ask, then you can have a doubt that this we just got an expression for the value of a state. So now why do we need to further decompose it? Why do we need something called Bellman's equation? Why can't we just simply use this? And that is because the previous examples that we were considering were very simple. They just had 2 or 3 states with a very simple reward system. But in reality, the environments that we would have to deal with would be very complicated, and the reward system would also be very complex. For an example, you can consider the game of chess. So you have many states, and the reward system is also comparatively complicated. So in such situations, using the same approach would not be feasible. So Bellman's equation would be used here. And this is the expression for it. As you can see, the first term here, Rs comma A, is the immediate reward. Immediate reward is the reward that the agent would get when it takes an action A from a state S. And this term is the discounted future rewards. And this we have an extra term over here. So this term is basically the transition probability. So what does that mean? That means that the probability of transitioning from state S to S dash by taking an action A. And this, as I've told you earlier, is the probability of selecting an action A from a state S. So this is the Bellman's equation, and this lays the foundation for reinforcement learning. And this is used in literally each and every reinforcement learning model. So now let us take a look at the derivation of this. This is like, let's just see it now, like no need to go deep into this. So first, this is the equation for value of state, which we had seen earlier. So we can separate it into two parts. And then we can use a law to replace y, x, and z by all these terms respectively. And then we get something like this. And over here, you can see that this term over here is basically the value of state. So we replace it by that. So over here, this is the value of the state S dash, that is the next state. And then we can combine these two terms. And finally, we get the Bellman's equation. So we have understood what the Bellman's equation is about. We have taken a look at its mathematical expression also. So now let's go back to the first example. And now let's apply this equation over there and then see, does our problem solve? So this is the example. So using that equation, we can compute all the values. And now let's see how is that done. So this is the equation. And S4 and S8 are 0. So this means that the value of state 4 and 8 is 0. And why is that? That is because these two are the termination states, and termination states do not have any values. So S4 has a reward of +1, S8 has a reward of -1. Both of these have value of 0, and all the other states have reward of 0. Now let's start computing the value of state. So we have taken the value of factor to be 0.9. So we'll be going backwards. That is, we'll first compute the value of S3, then S2, S1, S5, and so on. So for S3, what do we do is that this is the first is the immediate reward. So immediate reward is basically the reward that the agent would get when the agent takes an action A in state S. So the reward is what? In state S4, the agent would get a reward of +1. So the reward is 1 plus the discount factor, which is 0.9, multiplied by the value of the next state, that is value of the state S4, and that is 0. So the value of the state 3 comes out to be 1. And in the similar way, we can calculate the value for all the previous states, that is S2, S1, S5, and S9. So in S2, you can see that the immediate reward is 0 because the reward in state S3 is 0. And the discount factor is 0.9. And then we have multiplied it with 1, which is nothing but the value of the next state. That is value of the state 3. So, and that's 1. So we get the value of state 2 as 0.9. So that's how we calculate the value of the previous states. So using the same approach, we can calculate the values for 7, 11, and 10. But then what happens at state 12? So when the agent is at state 12, the agent shouldn't be going to state 8. It should be coming back to state 11. So state 11 becomes S dash, where 12 is S. So this is how it's computed. So the immediate reward, that is the reward that the agent would get when it takes an action A from state 12, that's 0, plus the discount factor, which is 0.9, multiplied by the value of the next state. So here our next state is S11, and that comes out to be 0.81. So we multiply it, and we finally get the value for state 12, that is 0.73. So this is how, using the Bellman's equation, we could solve that problem. So I hope you understood till here. And now we'll look at a sample program to understand this in a better way. So yes, just a second. Okay. So this is the code. So let's consider a map. So imagine you're at location F and you're driving a car, and your goal is to reach location C. So as a human being, which path would you choose? F to B to D to C. That's right. But then what happens if you have set your car to autopilot mode and you let the self-driving car take over? So in that situation, the agent would first compute all the possible states from F to C. So this is a reward matrix that does this shows all the possible states from F to C. So here all these rows represent letter A to F, and all the columns represent letter A to F. So let's consider the first row. So this means that when the agent is in state A or location A, then it can only go to state E directly. That is, you can see on the map also that when the agent is at state A, it can go only to state E directly. It cannot go to any other state. So that is what these ones and zeros represent. So one represents the state where the agent can go directly, and 0 are the states where the agent cannot go to directly. And similarly, in the second row, this tells us that when the agent is at state B, it can go only to state B and state F directly. And you can see on the map also that when the agent is at B, it can go only to F and D. It cannot go to any other states directly. Now, what does this 100 mean over here? So this is the third row, right? So this is basically when the agent is at state C. So when the agent is at state C, if the agent remains in that state itself, then it would get the highest reward. And why is that? That is because reaching state C is our ultimate goal, and hence that has the highest reward. Yeah, but if the agent is at state C, it can also go to state D. And similarly for the rest of the other states, D, E, and F. So this is basically the reward matrix, which contains all the possible states from F to C. And then Q is the learning matrix. So this is the matrix in which the agent will be learning and storing its rewards. So we create a matrix of dimension 6,6, and then initialize it to zeros. And then we take the value of gamma to be 0.8. We haven't taken the value of gamma to be 1 because let's consider an example. Suppose you're preparing for an exam and you don't know whether you'll pass or no. You don't know the outcome. So in such situation, your chances of passing are 80 out of 100. So taking the value of gamma to be 0.8 makes MDP and Bellman's equation realistic. So this is how it becomes realistic. So now we have this function over here, possible actions. So this function computes all the available actions that the agent can take from a particular state. And then we have this next function, that is action choice. So this function chooses at random which action to be performed from all the available actions. And then the main important part of the program is the rewarding of the Q matrix or the learning matrix using the Bellman's equation. So over here, the max value is the highest value in the reward matrix. Over here, the highest value in each line of the reward matrix. So here it's 1. So that's how Bellman's equation is used to get the reward matrix. And then we have, and then we run this process over n number of times so that the agent learns everything there is to find. And during each such iteration, the agent will detect its present state, will choose a course of action, and update the Q function matrix. So after this process is done n number of times, we get the Q matrix or the learning matrix. So now what does the learning matrix mean? So this tells us that over here again, the rows represents letter A to F, columns represent letter A to F. So when the agent is at state A or location A, then it would get a reward of 258.44 when it goes to state E. So as you can see, the agent can go only from state A to E directly. And on doing so, it would get a reward of 258.44. And then in the second row, that is when the agent is at state B, it will get a reward of 321.8 if it goes to state D, or would get a reward of 207.752 if it goes to state F. Now, why is the reward in state F lower than state D? This is because, as you can see from the map, when the agent is at state B, if it goes to state D, then it has an option to go to state C, which is our goal. But then if the agent goes to state F, then it cannot go to state C. And hence the reward of going from B to D is higher than going from B to F. And then we have the third row, that is when the agent is at state C. So here this is the highest value. So when the agent has state C, it gets a reward of 500 if it remains in that state itself, because that's our goal. Then yes, if it goes to state D, it also gets a reward of 321.8. Now what happens in such situation? What happens if the agent is at state C and then it goes to state D? So in such situations, you can see from the fourth row, when the agent is at state D, it gets a reward of 401 if it goes to state C again. So if the agent is at state D and it goes to state D, then it would again come back to state C. So this is how, using the learning matrix or the reward matrix, the agent will compute the best path from F to C. So that's it from my side. So if you have any doubts, feel free to ask, or you could just post it on the chat box. Thank you.
Okay, so as we can't see any doubts in chat, and okay, so there, hello, Alekya.
Yeah, hello.
There's some doubt in chat. What about state 6? In your diagram of that fire, diamond, and what? There's some doubt with state 6. So can you please go on that slide once?
Yeah, just a second. So the state, right? State 6. Okay, so state 6, that is basically a block state. So the agent cannot cross over that state. So hence hence the agent cannot go to that state, and that's why it doesn't have any value or any reward. So I hope this clarified your doubt. So
Okay,
if there are no
so
doubts, then yeah, I would like to hand it over to Shubham to continue with the session.
okay, so we will take a break of 5 to 6 minutes. After that, we will see some algorithms, some advanced algorithms, and the code for that. So okay, we will start our session at 6:27 again. We will resume at 6:27. Okay, till the time, I will clear Adil's doubt. Adil, see that state is block state. That is, you can assume that state as if suppose you are playing Ludo, then there is a fixed path that you need to follow, correct? Or so you can't move in that between rows unless until you have covered whole path, correct? So it in the same way that is some block state, like in a game of chess, your horse can't move straight, or your rook can't move in diagonal direction. So it's like that something. Hope you understood. Yeah, it was predefined. That's why its color was different than other state colors. Other states were of white color, then that was of block green color. That was a block. That's why. Raghav, your question is not pretty clear. Like what you didn't understand. Just a second. Alekya, can you please share your slides again? Hello, Alekya.
Yeah.
Yes, Raghav. So what you didn't understand? Binary part. In this equation, there is no binary part as such. Just a second. I will allow you to unmute. Wait a minute.
Yes, sir. Hello.
Yes, sir. You can unmute. Can you please speak? Hello. You can speak. You're allowed to unmute. Just saying, it's Raghav. Oh, wait. Yes, Raghav. You can like unmute yourself. They've allowed mic for you. Raghav, can you please unmute? Like we are not understanding your doubt clearly. You can unmute yourself. Okay, so Raghav, I think there is some issue with your mic. Okay, so we can resolve that later. Don't worry. Okay, so we'll start now. Is my screen visible? Can someone please confirm?
Yeah, it's visible. Yes, it is visible.
Okay. So first of all, let me give the let me let me learn just this. Okay, so starting with now we'll be dealing with some algorithms of reinforcement learning. So now things will be a little difficult. We'll move towards little advanced things. So it's not necessary that you understand everything. The aim of this whole algorithm part is this part the session of mine session is to give you an intuition of how these algorithms work, what is the importance of these algorithms, and to show you how to implement them in real life. Like we will see examples of a card pool that is balancing a pole on a card, how a reinforcement learning model learns on it how to balance the card. Then we'll see the A to C model, that is advanced actor critic model. in that we'll see this car example, how this car is learning on its own. So yep, so that's it. So with this, I would like to give little summary of the sessions that of the session that we had till now. So as we know, reinforcement learning is nothing but just we can understand this with an example. Like suppose everyone has saw this game of Takeshi's Castle, correct? So what used to happen here is there was a player used to enter from a door and used to find the right path towards the goal. Okay. And sometimes used to get distracted and sometimes used to get like go to the go to the another path. Then sometimes he would end up in this wrong paths or he might have missed the path. So what he used to do there is he used to find the right path, try to find the right path. So that that thing that the player was doing, that exact same thing is depicted by a machine learning model when we train it. So suppose that bot was an suppose that player was a machine learning algorithm. So what the machine learning algorithm was doing was it was trying to find the right path, and if it was getting right path, he was rewarded. And if the machine learning algorithm was getting into some wrong path, then it was trying to correct himself. Okay, so suppose that if it was not able to correct himself in a given interval of time, he might get out. So there was some penalty associated with it. Like like he might fail to come out of this maze. Okay, so similar thing is happening with a machine model in reinforcement learning. What is there in a reinforcement learning? There is an agent. This agent is nothing but that player that we had. What is action? Action is the things that player is performing. That is opening different doors and trying to figure out the right path to move. What is the environment? Environment is nothing but this maze. And one more thing is included in this environment is this player. Like these are these people who are trying to catch this player. Okay. Then there is a reward system and the state system. Then what is the reward system? If suppose he entered from right door and he came out of the right door, then he was getting some reward at every point. Like, he entered from this maze to here, from here to here, from here to here, and came out. With the shortest path, he covered he was able to come out. So he was getting some reward associated. Okay. And similarly, there comes state. What states are like he started from this point and he came out from here to here. So these all are states. Like going in any of this honeycomb is a state. Like honeycomb structure is a state. These all are states, different states. Correct. Now, what is time? Like what is r plus one? What is s plus one? And what is we talked about two things like this, like the session we were having as of now till now. There are two things were talked. The next the immediate reward that we will be getting and the discounted future value reward. Okay, so what is immediate reward and what is discounted future value reward? It can be understood in such way. If suppose I have entered in the right way, like right comb structure, that will lead to the right path. Okay, so that will discount me as of now. But suppose from here I'm coming to this last point, then this last point also has some effect on this path, correct? So that is my discounted future value reward. So in that way, reward system works. So I think I am clear with this whole things that we have talked as of now. So this is what reinforcement learning is. One more example, if I want to take is this example was taken before also. A child example, how a child learns. If suppose we depict a scenario where a child is trying to differentiate between objects, and that objects are nothing but fruits. Okay. So suppose you have kept two fruits, gave two fruits to a small child. What he will do is he will take one fruit and he will recognize that fruit as some if he picks up an orange, then he might say that as an orange or an apple. Okay, so if suppose he does that thing right, if he says yeah that is apple, then his parents might say him yeah yes you're correct, that is an apple or that is an orange. So that type of thing is nothing but actor critic model, where the actor is performing some action and the critic are nothing but the people, the environment that you have is helping you to get your knowledge base updated, whether the information that you process was right or not. Okay, so this was the basic summary that we had as of now. Is any doubt? Like, is any doubt in the chats or is any doubt? So you can ask. Okay, so I can't see any doubts in chat. So we will move now We'll now deep dive into the PG, that is policy gradient. Policy gradient is an algorithm that help us to solve machine, like solve the reinforcement, like solve and implement reinforcement learning in real life. Okay. So what policy gradient is, first of all, let's understand that. Policy, as we understood from the sessions that we have until now, policy is nothing but a cumulative of states, action, reward, and the environment that we have. Like suppose you are playing a chess game, okay, and that chess game you made a move. So after that move, anything that is happening, that is whole episodic thing that is considered into the policy. Like let me differentiate between an episode and a policy first. So suppose you are playing a chess, you made a move. Like suppose there are two horses, you have one horse and one knight and one rook. Okay, if you move right knight, there are some certain actions associated with that, correct? There might be some this game might turn into some other track. Okay, and if I move a rook, then this might go into some another track. So this two tracks that the whole game has changed is called episode. That is one episode. Like the probability of different things happening after this thing has happened is called an episode. Okay. So and the whole thing that is done is a policy, like how the things were implemented, like how the paths were taken, that everything comes into policy. Okay. So we have two things. One is policy and one is value-based system. So policy-based system focuses more on how the rewards are being paid and how the states are being used, like how the states have been like transmitted and test passed. Okay. So in that way, policy works. So now more going the reward system, how reward system works exactly. So this is a reward hypothesis, this main thing that we have to see. So the most important thing in the reinforcement learning is a reward system and the state system, obviously. So what reward system is? The whole idea of the machine learning algorithm in a reinforcement learning is to maximize the reward. You implement any algorithm in reinforcement learning, the main objective of it is to maximize the reward. Correct. We talked about this equation before also. This equation is nothing but a generator function that says that the reward is a generator function that is cumulative of all the rewards that will be made available to us if we make certain actions. This is the next immediate reward, and this is the next to next state reward that we might get, and similarly goes on. If here you see this gamma function, this gamma function is nothing but is the value lies between 0 and 1, and it helps us in decreasing the reward function dependency on the further states. Like if suppose I am getting a reward, then that reward must be more dependent on the next state. Correct. Like suppose if you are playing a chess game, or so the next move of the opponent, on the basis of that only you have to make your own your next move. Correct. So that is a reward system. But in the same reward system, you will not wait for you will not think of the last move that the opponent will make. On the basis of that, you will make some move as of now. That is done. That is done. But that dependency is very less. Very less. So in that way it works. This gamma function is nothing but a discounted return function that help us to decrease the dependency on the rewards that will come after 2-3 steps or after 4-5 steps. Okay. This value is fixed by the developer, or it can be find out by some machine learning algorithms depending on different like hit and tag method, like trying different methods on it. Okay, so we have talked about MDP, that is Markov decision process, as you know. So here's some terms that we need to again refresh that will be used in our codes are this S and ST and ST+1. These are nothing but the state space. They belong to space. This AR actions, this RR rewards, and GT is nothing but a discounted return function. Okay. So if I say in simple words, MDP defines probability of transiting into a new state, getting some reward. Just a second. Yeah, Raghav, so don't worry. Focus on this PG part first. We will get to that. Okay. Okay, so I was talking about the MDP function. So what MDP is, that is Markov decision process is. Markov decision process defines the probability of transiting into a new state getting some reward given the current state and the execution of an action. I will repeat. MDP function defines the probability of transiting into a new state. That is from getting into a new state from the state that you are in. And there is some reward associated with the current state and the execution of the action. So that MDP is okay. So if you see this equation is really very pretty simple. Like here in this equation, there is nothing like the state are just the next state. The next states are taken into consideration, but that is not a solution every time. Like you have to consider many other states also. Like if suppose you are, suppose let's take an example of games like the games that we play. Suppose Call of Duty or PUBG, then there the agent is the player itself. The environment is the environment that everything the player in which the player is. So there are different states that we have. Correct. Like we can move forward, we can move backward. So on the basis of that, still many things are defined. So in that way, this things work. So this is the first order. This equation is nothing but a first order Markov equation. So it's a very simple equation, but there are many things associated with it. We will look ahead as we go. Okay. So as I was talking about this gamma, that's nothing but a discount factor. Remember this thing, but this gamma will be very useful, guys. And one more thing to notice about this gamma is with every next reward, that is, this is a reward in the next step, this is a reward in the next to next step, this is a reward in the next to next step, that is the third step. Every time gamma is being squared and the value of gamma is between 0 and 1. Okay, so if I square a value that is less than 1 and between 0 and 1, that value will decrease more. Okay, so even this gamma value is decreasing the whole term. So in that way, as it was said, after some point of time, everything will become it will not become completely zero, but yes, it will converge to converge to zero. It will be a converging curve that you will be seeing. Then one more thing to observe here. Okay, no, so one more thing to observe here is this small p. What this p is? This p is nothing but the dynamics of the environment, and this dynamics of the environments are outside the control of an agent. Okay, like if you're playing a game, if you're playing PUBG, you don't know what the dynamics of the environment are. You don't know where the other players will come from, where you will get the fire. Okay, so that is not in your control. Okay, if I take one more example of this, is for explaining this equation more is, if suppose there is wind, you are standing in a windy area and there is high wind flowing, and you're unable to walk correctly, okay, and you're standing in a position. So the next step of your will be defined by the wind pressure that you're facing, and it can be in any direction, correct? So that thing is nothing but that small piece, nothing but the dynamics of the environment in which you are. Okay. So that was about this equation. As we have seen this equation before also, we will now move ahead. One more thing to highlight: when an agent follows a policy, it generates sequence of state, action, and rewards called the trajectory. Please keep this thing in mind. That's the word trajectory. It will be used ahead. So I will explain this line again once more. See, there is an agent, and he is following a policy. That is, he is following a probability path. Okay, like he is taking a path that is probabilistic path. Policy is nothing but a probabilistic distribution of the things that are in the path. Okay, so when agent is following a policy, he will go to some states. He will do some action on the base from that states, correct? For going to another states or for doing something, and on the basis of that action, he will get some rewards, some penalties, etc., etc. This all thing is called a trajectory. And why this word trajectory is important is because when we will deal this thing in code, this trajectory is the thing that we have to deal with. Like we have to use gradient ascent. We will not use here gradient descent. Gradient descent is a function that helps us to decrease the loss. Okay, like we decrease the loss on the trajectory. But here we will use gradient ascent. Why we will use gradient ascent here is because we want to maximize the return, the profit, the reward you have to maximize. Okay, so this trajectory will be used there. Okay, so now coming to policy. A policy is defined as positive distribution of action giving a state, as I said just now. So see, this is nothing but a policy, that is the action in the state. This policy is based on the action in the state. Okay. Okay. So now let's deep dive into policy. See, this equation represents the expectations of this of all the policies. And this R here, this small R says about the all the rewards that we have got in this trajectory. Okay. So if we highlight this equation more, like if we focus on this equation more, so as we know, the objective of the reinforcement learning agent is to maximize the expected reward. Then while doing that, we are following a policy, correct, for maximizing the expected reward. So there we use a parameter theta. We define a parameter theta, and this parameter theta is nothing but coefficient of complex or the weights that we'll be using in deep neural network. So understand one thing. All the things that we have been talking as of now, this all things were in theory. But when you want to implement these things, this neural network, this reinforcement learning, you will either use neural networks, or you will use some algorithms like this, or you will use some architecture for it. Okay. So suppose I'm using a neural network, then this theta is nothing but the weight, the bias of that neurons in the neural network. Okay. So that is the parameter. So that is the theta. This is nothing but a complex weight function, bias unit in the neural network. Okay. So my main aim is to like the main aim, if we represent this total reward for the given trajectory as this RT, here the RT, we arrive at the following definition. That is, this J of theta is equal to expectations of all the policies that we had into a reward for that whole trajectory. Okay. So with that said, or with that said, this is the equation that we have to basically work on. Okay. Now, all the one more thing to see here is all the five MDPs, that is Markov decision process, have at least one optimal policy. Okay. And among all the optimal policies, at least one is the stationary and deterministic. So what this line means, see, we saw about the example of Takeshi's castle. Okay. So there was one policy, there was one path that was the most optimal path. Like if you follow that path, you will get out in the least amount of time and with the highest reward. Okay. So that is nothing but that is nothing but the optimal policy that we have. So this line says that all the Markovian decision process have at least one optimal policy. Okay. And at least one of the optimal policies will be stationary and deterministic. See, what this stationary and deterministic two words mean here is, above when we saw this example of Takeshi's castle, there the whole scenario was not deterministic to a player who was playing it. Okay. But when he started to go on an optimal policy, when it took an optimal policy, it all became deterministic to him as he came out. Understood? So in that way, this all things this line means. Okay. So now here comes the gradient descent. And as of now, we will here use gradient ascent because we want to maximize the profit. This theta, as I said about, this is nothing but the parameter of weight for the complex neural networks. So this says that weight or the weight bias for the next time equal to weight bias for this current time stamp plus some learning rate multiplied by the reference of j theta t. This j theta t was nothing but this term. Theta t was nothing but expectations of all the policies into the reward for trajectory. Okay. So in that way, this equation has been derived. Don't worry if you don't understand every point of the every part of this equation. These equations are a little tedious, but like focus on what we are saying, so you can get as much as you can. So now, but there comes in challenge. Like there are some issues with all these things that we have to. So the first thing is, how do we find this gradient of the objective about which contains the expectations of these expectations? So there is no way to find the gradient, correct? Because there are some integrals involved in this, and these integrals will be very, very tough for us to compute. Even because as this is converging integral, at some point of time it will become stable and it might go to zero and it might lead to problems for us. Okay. So for that reason, there are few changes that we have to do in this equation, and these changes are nothing but introducing a term that is called bias term. This B term, that is a baseline term that will help us in our future. Okay, so so as I talked about, there was an issue with this thing, so it will be solved ahead. So now coming to this policy gradient theorem, nothing but the same thing repeatedly. This says that the derivative of the expected return a reward is the expectation of the product of the reward. This expectation of the product of reward into the gradient, this triangle gradient into the log of the policy theta following the trajectory t. Okay. Now what we have did is we have just expanded this project trajectory t, and this trajectory t is nothing but capital P times S naught, that is state 0, and addition of all the addition of all from going from time t1 to all the time for all the policies at every state, all the actions performed with small p st plus 1 rt plus 1 stn comma at, that is state t plus 1 and the reward t plus 1. So I will explain these terms once again. So this P represents the error distribution of the start error distribution. There's nothing but the probability distributed for all the states. Okay. Then this as we know, A is the action, S is the state. So okay, so we'll come to this equation that we are using ahead. So what we have here is we have just multiplied log to it. When we multiply log to it, everything comes to log. This thing comes to log, and as there is a multiplication, it all goes to addition, and then we have just made this equation, like plugged in everything into this equation. So this is the final equation that we have got. Okay. And but there is one more thing. Here we have this thing is called model free algorithm, because we don't have model the environment. Like see, here there is no parameter in this whole equation that talks about the environment as such. There is A that talks about the action that we would need to perform. There is S, that is the state that which we are in. There is R, that is the reward that we'll get. There is T, trajectory, that is nothing but the policies that we took, the rewards that we got in the policy, in the state we visited, and the action we took on that state. And this is nothing but the expectations of all the policies. Okay. So there is no model in this formula. So this is called model free algorithm. Okay. So now let's talk about this trajectory, because this trajectory is the main important thing that we have to work on. So this trajectory is nothing but the gradient descent thing that we have to work on. Like we have to decrease it, increase it, we have to differentiate it and integrate it. Like we have to mode it in such a way that the reward is maximum. So as we know, this was the equation that we had. So there was problem with it, and the problem was variance. So what exactly variance is? What all these things were, like all these things, if I summarize, like all these equations that we saw. So suppose, let's take an example. I'm going to see an example of chess. Okay. If suppose you are playing chess, you have two options. Your opponent have made some move, you have two options. The first option is to move knight, and the other option is to move rook. Okay. If suppose you move knight, then there is a policy fixed. This is the path you're going to take. There are some episodes associated with that. And all these things, all the learning that we'll do in this path will be kept with you. Okay. Now suppose you're doing this is all the learning is with you. Okay. Now suppose you are moving your rook. Then again the policy is made. Again episodes are made. Again the state action reward things are set up. And there is some learning that your model have done. Okay. Then these two learnings that you have, this can't be integrated. Like you can't use them both together. So that is the biggest problem we have. That is, this problem is called vanishing gradient problem. That is, if you suppose took a policy and then you went into the policy, then you can't change. Like you can't come back and say, okay, this was, if I change this thing, my algorithm will increase like that. Like you can't change the whole policy. You can change episodes, but you can't change the whole policy. So that variance is very high in these things. These trajectories, you have very high variance. Like you have 4 or 5 trajectories, but the variance associated with all the trajectories is very high. What I mean to say is, if suppose that you have moved your knight, and that knight will make you win the game, but if you have moved the rook, it might make you lose the game. So there is high variance in both of this path, because one is making you giving you high rewards, and other one is giving you negative rewards. Okay, so this problem is to be dealt, and this problem is dealt by a process that is called Markov chain Monte Carlo, that is MCMC. Okay, or we can say that we can say one more thing about this is this MCMC. It's a little advanced thing. Okay, so we'll not focus on that like very depth. We'll continue with the other thing. So this was the basic thing. Like there is a problem that is that you have to deal with, that we'll see ahead how the other models algorithms deal with this problem. Now there comes reinforcement with baseline. Reinforced with baseline. So to iterate the reinforced algorithm computes the policy, it tries this. Okay. Now one more thing to observe here is observe in this equation above was the equation that we got above was that we didn't have solved the problem of variance. There was problem of variance, correct? So what we have to do is to solve this problem, we introduce this MLE. This MLE is nothing but maximum likelihood maximum likelihood estimate. What does this does is it is it is well known that the data overwhelms the prior. In the simple words, like what it does is it just sees all the data, the nearby trajectories data that it had, and it figure out some amount of how to decrease the next amount of information to decrease the variance that it has. So suppose like if I give you the example of it, suppose the same example when you were playing this group and the uh, thing about this like average reward system, like if you win first reward, reward, the average of it, what you can do is you can just subtract that reward from your generator function. What this thing will does is this thing will help you to map your path correctly. This might be a little tedious to understand how this thing is happening, but as we will see code ahead, it might be easy to understand. See, what is happening is by this term we came here in this equation is this base nothing but the average, like the average of the rewards that you had, like understanding in such a way that it was an average of the rewards that we had. If suppose the rook was making you win, then you are getting a positive reward, and the knight was making you lose, then you were getting a negative reward. If you know the average of both of this reward, you can just do is you can club that average, you can just subtract the average from the generator function. Then this whole equation, the whole theta that you will get will help us to find the correct path. Okay, so this was about the reinforcement baseline. So we have done nothing, like we have just opened these terms and we have just derived it and just shown key how it works, proved it. Okay, so that's it for the theory part. Like these things can be found online also. Like you can look into it. If you have any doubts, you can come to us. These things are little tedious like, to understand. Okay, so okay, now let's see some applications of what we have did as of now, like the policy gradient. So this is a card game. This is the card game, card pool. What is happening here is it is trying to it is trying to keep this pole on this card like still. If the card moves, it's just balancing the pole on it. Okay, if the card moves left or right, the pole will fall. Okay, so this card is trying to move left and right according to the pole to balance itself. Okay, so this is some code part. Like I will explain I will just give the intuition of how these things are working. Here we have just imported some libraries. Here we have made an environment. This game environment has been made. This is from the OpenAI gem, where there are 4 or 5 environments present. You can use any one of them. So the environment that we have used is cartpool. The cartpool as you saw below. This has nothing but the observation space, action space, and threshold that has been printed. So this is nothing but the observation space, like the thing that you can observe in the environment. Then the action space that you have and the threshold that we have. Threshold is nothing but the reward speed, like reward space that you have. Okay, so now coming to this thing. This thing is a main model, like how the model is been made. So here we can see some things like hidden size 256. This is nothing but a neural network that we have built. This neural network consists of a linear like linear. It has ReLU, that is rectified linear unit. Then there is again this linear layer which consists of 256 hidden neurons in it. So in this way, whole model is made. Then we applied a softmax function. Softmax is nothing but just to scale down or scale up the things. Okay, like to bring the things into a specific value. So we have replaced dimension to bring it to a specific value. Okay. And one more thing to know like one more thing to see here is this model is linear twice. Like it contains two linear layers. Okay. And a ReLU function that is linear linear unit. Rectified linear unit. Okay. So this is the model that we have made. Um, so we have just printed the model. Okay. Now this is the training loop that this is the main loop in which the training of the whole thing is happening. So I will go one to one thing. I will explain one of the things. Uh, okay. So this thing here says the learning rate. Learning rate is nothing but the alpha that we saw in this equations above. This thing will show the alpha. This alpha that we have here. This alpha is the learning rate. Your learning rate must not be very high and it must not be very low. Because you have a very high, if you have a very high learning rate, then there is a possibility that you might miss the maxima point. And if your learning rate is very low, your computation power might be hampered. And there are many other things associated with it. So you can put hit and tell and you can find the best learning rate. This is an optimizer, Adam optimizer that we have used. There are different types of optimizers. So we have used here Adam. Adam is just using this learning rate and the model parameters that we have given to us, and it is optimizing optimizing them. So we have here fixed the number of trajectories. I hope you all remember the trajectories that we used there. Trajectory is nothing but the cumulative of policy, state, action, and the reward that we have. Okay, this is the horizon. Like okay, horizon we'll talk later. Because, it will come as we move down. Uh, then the main thing that we have here is the gamma that we have. The gamma is 0.99. The same thing that we had here. The gamma function that was associated with every reward step. Okay, so yeah, this is the score that we have just instance this. So here it goes the trajectory like the trajectory loop. So it sets up the current state. So as I said, in that game we had look and the night. So here also we have different trajectories. So every trajectory will have some current state associated with it, and it will start with the current state, and it will make some assumptions for it, and will save that assumptions for it. Okay. Uh, then we have uh, then this then we have just called the model that we made above, and the actions are performed on the basis of this values that we got from this model in the current state, and then the previous state was known to us. So this all things is used for calculation of our rewards. Okay, so after doing that, this scores are appended into the test of the transition list and this score list. So after doing that, for all the 500 trajectories that we had, after doing that for every trajectory, we got the whole reward system here. After this all thing that this all part of code is nothing but it's just here. This part of code is nothing but just optimizing the values that we have. Here here it is for calculating the loss function that we are printing the average loss that we are printing, and here in this part of code here we are doing nothing but we are just calculating the batch. We are creating batches and we are training it. Like what we are doing here is for the trajectories that we have. Hope you remember that I talked about this reward B term. So that B term was nothing but the average of the rewards of the trajectories, correct? So that is the value that we are calculating here, and then we are just plugging everything inside, and then for every batch of trajectory, we are finding the average score for it. So as you can see here, as we are moving ahead with the number of trajectories increasing, our average score is getting better. So that is nothing but our cart is learning how to move right, how to move right. Okay. This everything is nothing but just to plot these values, just to plot this value. So this is a trajectory duration, and this is a trajectory approach. With every number of epoch, the duration has increased, and the reward system and it has got better. Okay. So this is nothing but this part of code this deals with the display of the uh, display of this image in our collab tool. So it is not a part of code. This is a watch agent. It does nothing but just use this model that we have made above to put this card pool environment into it and just to show it. So if I run it, just a second. It can't be done. Just Okay, so it might take time, I think. Okay, so I have to run everything from my just a second. Okay, so in time it's running just a second. I had the training period process. So directives have been trained. Okay, so is there any doubt as of now? If you have any doubt, you can ask it. You can unmute and ask.
And type your doubts in the chat.
Yeah, you can even type doubts in the chat. Okay, so till that it runs, as we are short of time, we'll go ahead. As it's done, we will come again back to it. Okay, so that was policy gradient. So if I summarize policy gradient, it is nothing but suppose you are playing a game. Suppose you are playing a chess. You have two. Yeah, you have two options. You can move knight or you can move rook. If you move knight, all the policy has been changed. The whole trajectory now that you will have will be deciding again. If you move rook, the whole thing has been changed. It will be deciding the game again. There is a problem associated with this thing about with this algorithm, that is vanishing learning that you had. So exactly happening here is, if you have moved rook, so you can't think now, if I move at night, then what the scenario should have been. So that can't be done now. So that is the vanishing problem of the trajectories that we face in policy gradient. So okay, so it started. Huh. Okay, so there was some crash. Okay, so it will take time. We will run it in the last. Okay, so that was PG. This policy gradient. I know this algorithm is a little tedious to understand because they have many things involved in them. Okay, so what can be done is you all can you all can watch the session again, or you can find resources online. And if you don't understand anything, you can come to us. You can come to our Discord channels for this. Okay. Now coming to the last part of this of my session, that is actor critic method 8 and 8 to C. So why this A to C is important and what exactly A to C is? See, in policy gradient, you were having some, like, you were knowing how to proceed. Like, you were having a fixed amount of policies that you were like the fixed. If I say in simple language, then there was fixed number of inputs and fixed number of outputs. You can assume in such way. Okay. Actor critic method is used when you don't have fixed amount of inputs and you don't have fixed amount of controls in your hand. Okay. So there the actor critic method is used. The actor critic method is based on actor critic method uses two things: the policy gradient method and the value gradient method. That is these are the two part of algorithm, the different type of families of algorithms. Both are used in this A to C. Okay. So if we see the problem with PG was there were glaring issues. The vanilla policy gradient, noisy gradient, high variance. As I said about because the learning was totally vanished from one after one following one trajectory, the trajectory learnings were vanished. And beside high variance gradient, other problem was the trajectory theta. Because if suppose the cumulative worth becomes zero, then the all trajectories will come down to zero. Okay. Now the next thing that comes is the solution. Like, what solution we have for that? So there is this. We can use this thing. Hope you remember that we subtracted B from GT. Now we are subtracting B from GT, but with the state with having state in mind with B. So what we are doing here is this B, that was the average reward like thing. It is now used with the state in which it is, and on the basis of that, the theta is calculated. Okay, so what exactly happening here is what, like, if I differentiate between the PG and A to C. So in PG, there was only the agent that was doing everything. It was figuring out different part. On the part it was completely going, it was finding the value. Okay. And in A to C, what we do is there are two things we have. There is one actor and there is one critic. What the actor does is it does the action in the environment. The critic observes the action of the agent in the environment, and on the basis of the action that the actors perform, helps the actor to improve himself by giving him some suggestions, you can assume. Okay. So in that way, actor and critic are. So actor and critic can be understood like the student and a tutor, student and a tutor. Okay. So this is the equation that comes out after all the things. So this is nothing but the expectation function for state zero, all the actions associated with the state. The gradient of the log of the all the thetas that we have from time zero to time t, all the policies that we have, and using them and then find this final equation. Then one more thing that we have to look here is this function. This was the same thing that was taught before also by Alekya, while she was explaining the Q and the V value. Okay, so using the Q and the V value, we can find A value. This A value is again nothing but you can understand this is nothing but a critic value that a critic uses to find the state and the action that how it is performed and how the actor must change it or the actor must perform the next actions. Okay, so again coming to the code part of A to C. So in A to C, we will be demonstrating this card play. So what this card is doing is it's trying to come to this uphill. Okay, come to this final fact. So as you can see here, it is not moving as of now because the iterations on which I've trained is less. So here, if I increase the number of iterations, here, if the maximum episodes are increased, if by 2000 to 20,000, it might get more train. It might get better. Okay, so this code will be shared with you all. You can try this code on your own. So I will explain the important things of this code. Just importing the models, then making environment for this mountain car. Say this nothing but how we are sampling the things. So randomly sampling the things. Then this is the this is the architecture. This is the actor critic architecture that we have made. It contains dense layers, hidden dense layer, hidden dense layers. The number of hidden units are to be given. So here it is 128. As of now, the activation function uses JLU. So this is a common that is both in actor and critic. Then there is an actor layer, there is a critic layer. Okay. So this model is made. The model is actor critic model with number of actions. So it is called here with the environment action space dot n, that is to here, that is to go up go in like go towards the flag or come backward. Okay, so in that way this whole thing is made. This is the steps that are taken into these are the steps that are taken, the states, reward, and the state actions that have been performed. uh, then these are the episodes. These are the episodes, as I said. After every step that you take, all the steps after that are a probabilistic distribution. So that whole path is called episode. Okay. This is also this is the whole episode. So it is converted into batch tensors to fit into the machining model, to fit into the actually deep neural network, and to get out the values. Then we have just printed the predicted expected returns that we will get, like the values that we will get. And here we have just computed loss to print the loss that we are facing, the loss that we are facing to increase to have a tune our parameters. Then this is an optimizer function, that is Keras Adam optimizer, again saying with learning rate of 0.01. Even this learning rate can be changed to see how the things work. Then the returns are calculated on the basis of the returns in the gamma function. As you know, the reward in the gamma function was used to calculate the GT, the the GT expected return function, the genital equation. So everything is calculated and epochs are given, like the number of epochs are 100. For every 100, it must give for every 100 citations, it must go 2000. And for every episode, it must go to the maximum 1,000 steps. That is defined. Like if I start or if I play a chess with the rook must the after the rook only 1,000 steps must be made, like not more than that. Till that only you go. Gamma is defined again. The threshold and the running award is given. The running award is starting with 0 and it will be increased as we go ahead. So in that way, for 2,000 iterations, it is calculated, and the average reward comes out to be negative minus 200. So this is nothing but due to the less number of iterations that we have done. As we increase the iterations, it might get better. These are the current learning things. So the episode reward is -20, the learning rewards were -20. Okay. So this code is just equal to render the image in Polar. So this image to be rendered, and this is the image of this cart. It's trying to move up. As it's going back, it's realizing it, and then it's again trying to move up. So if you increase the number of iteration, it will go up and come till this point. So this can be an assignment for you to hypertune these parameters that you have above, and to try to bring this cart towards its flag. Okay, so I know the session was this part of session was little tedious to understand. So if there is any doubt or if there is any question, you can ask in the chat also, or in the you can, if you want to unmute it, you can give you the option to unmute also. Okay, so I don't think there is any doubt. Okay, so I'm stopping the screen share. Just a second. Just a second. Okay, so all these things will be shared with you. The collab file and the PPTs will be shared. So try to do the things that as been told. So it will be useful for you ahead. Now we will now we'll see more. We'll see two more algorithms. We might go half an hour up. So I will hand over to Jenson. Jenson, please continue.
Okay. So, hello everyone. I'm Jenson, community mentor at SMLRA. So, I hope you guys understood everything that was taken up so far. I'm going to take is Q learning and deep Q learning. Give me a second. I'll share my screen. Okay. Am I? Is this screen visible? Shubham,
Yes,
can
it
see the
is.
slides?
Yes.
Okay. Okay. Thank you. So we are going to see what is Q learning. Okay. So these are the things which I'm going to cover. So I'm just I'll try to finish it off as soon as possible. But bear with me. It will be worth your time. So what is Q learning? The Q in Q learning, it stands for quality. So again, we have the Q components of a Q learning here, which is there's an agent here. It needs to perform an action on the environment. By performing any sets of actions, it will reach some state, and those states will give some of the rewards. By measuring the rewards which are given by taking some action at a particular state, the agent will get the feedback, whether it's a positive reward or negative reward, based on a series of loop. It will decide what is the best action that needs to be taken. So that's what we do in Q learning. We find out the next best action given the current state. So Q learning, it is actually model free. It's called model free or off policy. It's because it doesn't follow a specific policy as such, but it analyzes all the set of actions possible, and based on that, it tries to find out what is the best set of actions that the agent can take. Initially it uses trial and error, and then it keeps on increasing its accuracy. So what is the examples of Q learning in real life? So you can see like advertisement recommendation system. So like if you click on some of the like if you buy some TVs and you click on the TVs, so it will get a reward. It will get like a quantifiable amount of reward that you like TVs. So that is why it will recommend you more related products, like more TVs it will show you. Okay, so that is how Q learning is used in advertisement. So what is the agent environment system in reinforcement learning? Reinforcement learning, the agent environment already, my colleagues have already taken what they are. Just to brief you all and how it is used in the Q learning. So of course we know there's an environment. Environment can be a game, It can be anything. Any environment. It can be a game like a just be a simulation of a human body. It can be any kind of simulation, anything where you have an agent or you're a player, and it will you can do some set of actions. So it will give rewards, positive, negative, as we know. The model will try to find out the best strategy or policy. For example, we have like here a like game of PUBG. So in this game, the entire game is an environment. Whatever your player can do, that is shoot, jump or move or duck, all these things are the actions that you can take. By taking some actions, you will reach a certain location or you will reach some a different position. So that is your states. Just in this game, the states are taken by the images, the screenshots, which the which the model takes at particular intervals. So it understands where it is in the current game. And like if you see like an aimbot, how do you make an aimbot? So it takes a screenshot at and it sees what is the best sort of action it can take. So if you get hit, you will get the model gives a negative reward. The environment gives a negative reward, and if you shoot another player down, then it will give you a positive reward because your aim is to be the last man standing, to not get killed but to kill everyone else. So that is how the reward system works over here. So we have seen how Bellman equation is there, how Markov decision process is there, and we have seen these algorithms in detail. But how is it used in Q learning? Just a brief. So there's a in Q learning there is a simple thing called a Q table and a Q values. So basically, if you have if you are in any particular state, okay, so you will find a series of actions that will and these series of actions will give you a particular Q value. For example, if you're a player over here, then suppose initially it will shoot randomly in the map. It will shoot anywhere. It will not hit anybody. So that will give a zero or a negative Q value, and that it will we will see how to calculate those Q values. But it will give those values, and if it hits a player, it will give a positive Q value. So when it gives a positive Q value, the model will optimize. Okay, so I need to shoot more players. So that's how it's optimizing. And in this Bellman equation, we can see how the Q values are being calculated. The new Q values is based on the current Q values plus alpha times, that's learning rate, that how fast the model learns, times the reward which you're going to get at the next particular state. For example, if you shoot a person, so what is the reward you're going to get after you do that particular action? Rate. This discount rate is to understand that the immediate rewards, if you shoot a person first, you'll get a more reward. And if you take a lot of steps, if you do a lot of time pass and then you shoot it later, you should get a lesser reward. So that is why there's this discount rate over here. So the more number of steps you take, the discount rate will go lower and lower and lower. That's how it works, and subtracted by the current Q value. So you want to see how your Q value is increasing. So where in this while you multiply by it, when you multiply by alpha, you subtract the Q value, current Q value. So that is how the new Q values are calculated. And as Shubham already mentioned, the learning rate determines how fast or slow the model will be learning. All those things we already know. How is MDP used over here? Now look at these two. Look at these two. This thing. Images over here. So the blue is the starting state and the red is the final state. These are the two different scenarios. Okay. So in this case, this blue, we need to trace the path such that we reach a so if you see in this image, you have to take a general direction left. You need to generally take a general direction of left. That's how you will reach your red state. If you take all the possible set of actions, then you can see, just a second, I'll take a point over here. It will go from down, it will go from the sideways. Maybe it will reach that, or maybe it might not reach that, but it will take a unnecessarily a very longer path. So instead of doing that, if you go in the general direction of left and then you navigate, or you find out where is your ultimate penultimate state, or where is your final state. From there, you trace it back. Then you blue dot. That will be easier. So that's how Markov decision process is used. It finds the it calculates the Q values to the states which is closest to the penultimate state, and from there it traces down to the starting state. So important terms in Q learning. So these are the terms which you're going to use here. State is the current position of an agent, where your agent is currently is. For example, if you're in a if you're in a is any part of a game. So where are you currently in the game? So that is your state. Action is what is the action which you are going to agent is going to take when it is in a particular state. So when suppose you are in a particular area, you can take an action of going forward, or when you are in a different area, you can take an action of going back. So at every state, there's a action which you can take. So the state action there, that's why we call it state action pairs. So if you see, the Q values are given to state action pairs. So if you are at a particular state, and if you take this particular action at that state, then what is the Q values that are going to be generated? That is the Q values. Q values is just simply a number. Number which the higher the number indicates the state the action taken is a better action. It's just a number. Episodes is when you take a series of actions and you reach in a terminating state such that you cannot take a new action. For example, if you lose in a game, then you cannot play it again. It's like you can replay the game, but your entire thing it has ended. You cannot go forward or move back or shoot anything because your game has ended. So your entire state, the series of states or actions which you take when you are in the starting position till the end, till you reach the end, that is an episode. Rewards of course we know what's a reward, positive or negative reward, which the environment will give. And temporal difference is the formula which we are using, which we have seen here. This minus QSA, the current Q values is being subtracted. So that is the temporal difference which you are going to use. It finds the Q value by comparing the current state, Q value of the current state and the next state. So what is the concept behind this? Let's understand it very clearly. Okay, so the Q value, the formula of the Q value is as Q of S comma A for the Q value of a particular state at doing a particular action. It will give you a reward for doing that action plus the discount factor into the max slash Q of S dash A means let's just take this game. So for example, this is the frame, which is this is the place, and this is the state your game is. You can see the enemies over here. So if you want to shoot these enemies, so suppose if you go left, you don't shoot them, you go left. After doing left, what is the best action you can take? The best action you can take is aim and shoot. So that is the max, that will give you the max Q of S dash comma A. Or if you go right, then if you shoot, then it will give you a particular Q value. It will consider that you're taking the right, then you're shooting. So it will consider all that. And suppose if you shoot first, in the first time only if you shoot, then it will give you a higher Q value. Are you getting me? So that is how this discount factor is introduced. So what the actions you're going to take after that, what is the best action you can take? That is max Q of S dash command. Okay. I explained the what's gamma over here. And if you see, this is a iterative algorithm. It's an iterative formula. So it keeps on repeating. So the final thing looks something like this. Q of S comma A is gamma times Q S dash A plus gamma squared, because this entire gamma is, it will repeat itself. So it's like a recursive thing. So that's why this it will always gets multiplied. Gamma of Q S dash comma A, gamma square Q S double dash comma A. This is the first step you take. S dash is the initial current state. S dash is the next state you're going to take. S double dash is the next the state after the previous one. Like that till n states you're reaching, and A is the different actions you're going to take. So by this formula, you can see if you're getting a very positive reward after taking lot many steps, the final reward you're going to get is lower because it is after a lot many times. So that is how it is defining which is the best state. And this is the entire the formula. So as I told you, this is a iterative algorithm. So Q S comma A plus is equal to plus equal to this entire thing, alpha times this thing. So it always gets incremented. This thing is simply like Q S comma is equal to Q of S comma A plus this thing. So it's plus equal to this entire value over here. Alpha is the learning rate. RT plus 1 is the reward, as I've told you, and I've explained this. Max Q ST plus 1 is the state, the next state which you're going to take. This is the current state. This is subtracting that. So adjusting the value of gamma will diminish or increase the contribution of future rewards. So if you have a high value of gamma, So initially the gamma is 1 for your knowledge. Initially the gamma is 1. So it takes all the random possible set of actions. It sees what are the different rewards it's getting because the agent doesn't know about the environment. It needs to learn. So initially the gamma is 1, but then it keeps on decreasing and it reaches some particular value. It converges to a value, and then the optimal steps like optimal actions are taken. So I've mentioned what is a Q table. So in Q for calculating Q values, you need a Q table. Basically, it's just a like table where you have actions on one side and so this is how a Q table looks like. You have like in this particular example, you have the dog. You have to fetch the ball. So initially the dog is in the initial position and the ball is in the other side. So that is why if the dog goes over there, then the state has been changed. So for every state, there is a particular action which can take. So that is why there's this Q table. And this is the step how you make a good Q table. You initialize Q table, like you define put everything 0, choose an action, see what impact the action gives, and measure the reward. It will be positive. Update it in the Q table. Repeat it a lot many times till your Q table is ready. So like here, if you see the example, this dog. This dog needs to fetch this ball. So what it will do, initially, the actions which it can take is like it can stand over there, just stand there. It can sit down, or it can run. It can run and fetch, and it can come back. Various actions it can take. So if the dog is just standing there, or if the dog is sitting, you need to scold the dog. If you scold the dog, you give it a negative reward. And if it's going there, you need to give a positive reward. So that's how the model will learn. Okay, so with this, I need to take this dog and I need to go forward. I need to run and catch the ball. So initially, as I mentioned, for creating the Q table, all the Q values are initialized to 0 because you don't have any idea about anything. Then you perform certain actions. So if you in the start position, when you are in the start state, if you are keeping on, if you're sitting there, then it will give you a value. The environment will give you a value. So the environment will give, okay, so it's giving you a value of 1. It's giving you a lower value, or it can give you 0, it can give you a negative value. It will give some amount of value. And then you take another action and you check what is the Q value you're getting. So after some amount of iterations, you get a table like this. It will take some actions. It will check which is the best action. It will check what are the rewards it's getting, and it will fill this table. And after you have this table, you can see which is the correct action, or which is which set of action which will give you the highest Q value. So, and that if you take that particular action, you're reaching your goal. Okay. So this Q values is calculated using the Bellman equation, using this formula which I've showed over here. And after now understand this one thing. Initially, the dog is over here. It will calculate the Q values of all. It will calculate the Q values for all the set of episodes. It reaches some terminating state, and it will fill the table over here. It will find that this particular episode, that fetching is giving the highest value. So it will take that particular action. So the dog will come over here. Then it will see that catching the ball in its mouth, that is giving you also giving you a higher Q value. So again, it will update the Q table at every point of time. It will update the Q table, and that is how it is taking the best possible set of actions. So we are going to see in this, the example I've taken is the building grid world. So here there's basically a grid, and this is your start state. You can go right, you can go left, you can go up. Initially, you can't go left, but you can go everywhere else. But later, the numbers here indicates the wind. So here the wind is 0, so you can go aram se. You can take one step left. Here also you can take one step left. If you take one step left over here when it is 1, it will automatically go one step up. Okay. Similarly here, and here if you take one step right over here, it will automatically give 2 steps up. So that's how it's coming. So if you come over here, it will go one step up, it will go one step up, it will go 2 steps up over here. and then it will keep on 2 steps up, but you can't go any more up. So it will keep on going. And your agent, it needs to learn how to reach this goal. If you go from down, you won't be able to reach. You go straight, you won't be able to reach. You have to go up, you have to go down, and then you have to go back again. So the Q values are calculated for each of the blocks over here. Okay. So, and at every stage, it is checking the Q values. It's finding which is the highest one, and it's taking it. So we are going to see how using Python. So that was this Q learning this part. So let me just share the notebook. So this is how we are doing it. We have to install the OpenAI Gym. So we are doing that. Then we are importing the necessary modules over here. We are creating the environment. So we are create the environment. So environment will give you some rewards. So that's why you have to create the environment. What is the possible set of actions you can take? And what are the possible set of steps? So this is done by this code over here. Then this is creating the epsilon greedy policy. Now I want to mention that epsilon greedy policy is such that with a value of epsilon is a value between 0 and 1. Okay. So with the probability of epsilon, it will take a random value, and with the probability of 1 minus epsilon, it will take a best action. Best the maximum Q value. So this is the epsilon greedy policy over here. With the probability of epsilon, it's calculating what are the all the action probabilities. Here you can see, and with the probability of 1 minus epsilon, it's calculating what is the best action you can take. So initially, to see over here, initially it will go anywhere. It will take random values and it will see what is the reward it's getting. It's not getting any reward here because it's not going closer to the goal. But if you go closer to the goal, it will get higher and higher higher Q values, and the value of epsilon will decrease as you take more number of steps. It will keep on decreasing till it reaches again a constant. It will become you are going on taking the best sort of action. So initially the agent doesn't know what is the best action which needs to be taken. So it will explore. So that's why all the random it's taking random values. Okay, it's taking random steps, and then it will take the correct action after it gets Q values. Okay, and then you're building the Q learning model. We can see here the episode lengths, the rewards, which will there. Here the discount factor is 1. Shaded to 1, it will keep on decreasing. Alpha is 0.6. It's the learning rate which we are taking. It's also between 0 and 1. Epsilon is initially here defined as 0.1 over here. And here also in this code you have to understand one thing. After every set of episodes, you need to reset your this thing, your environment. For example, like if you play the like PUBG game, if you take a bunch of random actions and get killed, you need to reset it so that you take the next iteration. You see what is the next you can do. So that's why you have to reset your environment every time after every episodes. So that's what it's being done over here. It's calculating the rewards, and it's calculating the Q values, and it's giving you the next state which you can take. And this is the model that returns Q value and the stats. So you can go over here in detail. Since I have less time, I'm going very quickly. Here you can train the model if you do execute this function. It is plotting all the stats. So what you can see over here, I'll just explain what's over here. So this is episode length over time. It means that initially your episode is a very like episode length is very high. Means like your agent is doing all set of random actions. It's not going the proper place. It's running into some sort of loops or walking in circles. So the episode length is very high. But as it learns, as it takes more and more optimized value, as the value of epsilon decreases, as it takes more and more like a best sort of actions, then the till it reaches a constant value. And the reward, initially the agent is getting a very negative reward because it's doing random nonsense, but then it's taking better and better courses of action. So that's why it's reaching a terminating state where it is getting a fixed reward. Here, if you notice, the rewards are negative because it's taking like initially all the minus 175 is much more like lesser than minus 125. So like here the rewards, the optimal reward is minus 120, minus 25. But initially it is, so it is optimizing. You have to maximize the Q value. That's so after some time it will reach a constant. So the episode per time step, initially the episode is taking like the number of episodes per time step is very less because it's the episode length is very long. But as your time increases, it's taking many much more lot more episodes. The number of episodes is increasing, so you can consider, you can calculate many set of actions to find out what is the best Q level. So this is the Q learning part. I'll just quick to the deep Q learning. Give me a second. Share my screen. Is my screen visible?
Yeah.
Yeah.
Shubham, if you're there or anyone, can you
Yeah,
is my
it's
screen
Yeah, yeah.
visible? It is, right?
Yeah.
Okay. So now we have seen there in Q learning simple, there's a Q table. Okay. From the Q table, it's calculating Q values, it's finding what's the highest Q value, and it's taking that course of action. So if you have Q learning, then why do you need deep Q learning? That is the first question that may come to your mind. Why do you use it? So if you have like in the examples which you took, it had a few states. Okay, it had like 20 or 30 states, or like 10 15 states, and it had like 3 or 4 actions at most, going up, left, down, right, that much only. So the Q table is like the number of states multiplied the number of actions, because you're finding the Q value for every set of action comma value, action comma state pair. But imagine if you are in a complex environment where you can have like 10,000 states or and like 1,000 actions which you can take, then your table will be like 10 is long, like it will have like 10 million cells, and you need to update your table at every iteration and for every episode. So it will be computationally very expensive. It will take a lot more amount of time, and it will be unfeasible. So that is why you need to use deep Q learning, so that you can approximate the values, the Q values which are being generated. So we'll see how it's used over here. Before that, these are the contents which you're going to see. Where is deep learning used in? So you may have heard of DeepMind. So in DeepMind there is like it has created projects like AlphaZero and AlphaStar. So AlphaZero, it's one of the very renowned chess AI. So it's known to beat grandmasters. So it's a very good chess AI. And also AlphaZero, it has been it's good for playing shogi and go. And AlphaStar, it's good for playing StarCraft 2. These are the few games, and these are the two algorithms, let's say programs which finds the best sort of action. So this is your basically your reinforcement learning, this your where it's used in your environment. This chess, shogi, go are your environments, and these are your like this is your program which runs the code and which gives you the best sort of actions. And in some industry-ready applications like Google Cloud's AutoML and Facebook's Horizon platform, you can Google search and know more about these. So if you think like deep reinforcement learning is used in just games, so that's not true. It's used in many systems. It's used everywhere where there's an environment. So if you can simulate an environment of a human body, it can be used in healthcare. If you can simulate an education system, or you can simulate a classroom, it can be used in an education. It can be used for transportation. So anywhere where you can have a simulation and an environment, you can use these models to run and find out like what is the reach your goal. You can find out what is the best sort of actions you can take. So as I mentioned, the disadvantage of Q learning is that if you have a lot many states and lot many values, your the Q table, it will be very long, So the amount of memory, you have limited memory, but so you need to use your memory optimally. The amount of time is also limited. You cannot have infinite time, or you cannot have a very arbitrarily high amount of time. So that's why you need to optimize it. So deep Q learning, it optimizes this by approximating many of the Q values, okay, using machine learning models like neural networks. So difference between Q learning and deep Q learning, visually we can understand over here. So in Q learning, you have a Q table. For every state, action you input, you get a Q value as an output. If, for example, if your states are your rows and your actions are your columns, so for every state, action pair, it will give you a Q value. In deep Q learning, we don't have a Q table. Instead, we have a neural networks, and what we input is just the state. We only input the state for the neural network, and the output which it gives is the Q value and action pairs. Here you give both of them as input and get Q value as output. Here you give only state as input and get the value action pairs as output. And based on this Q value action pair, which of the action has the highest Q value, it will select that. Okay, that's the main difference which is there between Q learning and DQN. What is the steps over here? Now I mentioned that in DQN you have to approximate the Q values. Okay, so and you have to you cannot calculate manually. The computer cannot individually calculate all of the values, but it needs to approximate them. So how does it do that? So in DQN, you use like the past experience is stored by the user in memory. So for example, if you're playing a game and if you find a weapon which has a very high like if it does a very high damage, it does the most damage. So if you have a weapon like a bazooka or something, it does the highest number of damage compared to a pistol which does a less amount of damage. So the model will learn, okay, so if I use this bazooka, then I will get more damage and I can kill the opponent very easily, and rather than using a pistol. So that is how the past experience is stored by the user in memory. The next thing is the next action is determined by the maximum output of the Q network, which I mentioned over here. The maximum Q value that action which we are going to take, and how the loss function is calculated over here. So you are predicting the Q value, correct? So the mean squared error, which is just the target predicted Q value minus target Q value ka whole square, that is the mean squared error, that is calculated and that is optimized. So that's the loss function, and by optimizing the loss function using gradient descent or using other algorithms, you can reach the Q values can reach the target Q values. So the Q values you're predicting, it can reach the target Q values, and hence you can go forward and do the other calculations. If you see the Bellman equation we have over here, this Q s comma a is Q s comma a plus alpha times this entire thing over here. The section in green, it represents your target value. The immediate reward, the reward which you're going to get, immediate reward, plus the Q values, plus the maximum like Q values which you can get for the subsequent actions which you're going to take. So this is the thing which is affecting affecting your Q values. This is the thing it is increasing. That is why this is your target. So we need, this is your like the predicted Q value, and you need to optimize it such that it reaches your reaches your target Q value. Excuse me. So now, what is the issue of DQN, like deep compared to deep neural networks? If you see in deep neural networks, there's a particular fixed target. For example, let me give you a very relatable example. So suppose if you're playing a game, you want to get the maximum amount of fun or the maximum amount of enjoyment you can have in the game. So if you see, if you use certain weapons, it gives you a lot of fun. If you use certain characters, it gives you a lot of fun. If you explore certain regions, it also gives you a lot of fun. So initially the agent doesn't know anything, the model doesn't know anything, it will explore. It will see, okay, this particular weapon give you some amount of fun, and this it will give you some other amount of enjoyment, and so on. So the target is non-stationary. If you like you have you are not focusing only on the weapon or only on the region or only on the other parameters. Your target is it's non-stationary. That is why there is the issue that you're not directly able to like optimize and get the like the optimum value. So this is the issue over here. If you see this pseudocode over here for the DQN, uh, the target is reward plus the this thing max q of the further states. This q of further states, it can vary because when you take the action, when you get the reward, you'll understand, okay, so this is giving me higher q reward. If you're not taking the action only, you don't know what is the q reward, the q value which you're getting. So that is why this is a non-stationary target, but you need to optimize this entire target thing. So this is the which you are getting. So how do you solve this problem? The solution to this problem is by having two neural networks. Okay, so there's a target network and there's a prediction network. Basically, what your what your target network and prediction network is doing. Your prediction network, it's running your iterations. It is finding, it's giving the q value for all the possible set of actions. It's basically learning. It's exploring. And then after reaching certain number of iterations, like for example, like 100 iterations, it is swapping the weights and biases of the prediction network to the target network. Okay, so after like for example like 100 iteration, or this is a hyperparameter, this is a hyperparameter. After a certain amount of time, it is putting all the weights and biases in the target network, and that is how. And you can see over here the like this is the what is it? The mean squared error. So this value target minus predicted the whole square, and you're optimizing that. So if you think about in the with respect to the example which I mentioned, so if you have a lot of characters, weapons, regions, first you focus on the weapons. Okay, first you focus on the weapons. Which weapons give you the most amount of enjoyment? You fix that. You pick that weapon up. Then you go on to regions, exploring which regions give you the most amount of enjoyment. You explore those regions. Then you go using which set of using which characters it gives you the most amount of enjoyment. Then you pick those like in steps. So at iteration wise, you are getting the optimum value. You're getting what is the action which you need to take to get the higher values. So this is how the problem is being solved. Instead of there is one neural network, there are two neural networks over there. The second thing is that you can have an experience replay. So as I've mentioned, like if you have a certain characters, if you have certain weapons which gives higher damage, so you understand, okay, if I use a bazooka, it will be easier for me to there are many other parameters, but the damage it does is higher. It's the highest, for example. So that it will store in the agents, it will store in the memory. And when suppose you want to you find a target player and you want to kill the player, then it will say, okay, according to my memory, the bazooka is the best weapon to use. So it will use that weapon and it will shoot. Getting my point. So and here if you see, example is suppose it's a video game bot. So in this video game bot, suppose this bot is playing PUBG. So it will consider the last 100,000 frames and it will take a random batch of. Okay, so your enemy needs to move, your agent needs to move the screen, if you cannot take every frame, so you need to take a fixed amount. So this values they can change. Okay, so according to the model is seeing the frames, it's seeing your game, it's seeing where your agent is, it's seeing where your enemy is, and it's understanding where they are. And then it is finding, okay, I need to move the cursor over here. I need to press the shoot button, and that's how you're doing. So this is how like it takes up certain from the last particular set of frames, and those are given to the model, and the model finds out, okay, so this is the how to optimize the actions, what is set of actions you need to take. This is to summarize. These are the things which are happening. There's an agent. It initially doesn't know anything, so it starts performing some random actions. The environment will give you some observations. The agent will store its experience in the memory. It will give over the experiences to the neural network. It will give over the observation. The neural network, it will give the Q values. It's going to optimize, it's going to find the best highest Q value. And the parameters, which is the set of action and the states, they are going to be sent to the agent. So the agent will understand, okay, the next thing I need to do is take this action. So that will be the best action. Okay, again, to summarize, these are the steps it is taking. With a probability of epsilon, take a random action A. With a probability of 1, it is taking an action which has maximum Q value. Okay, and the game screen, the image, it takes a screenshot and it sends it to the DQN model, and it returns the Q value of all possible actions which you can take in that particular state. Okay, and as I mentioned, this is the loss. This is the target value, reward plus max, and I told you this is a non-stationary target, and how we have used student neural networks to optimize it. This is the loss function, subtracting it by the existing Q value. So your target and your predicted reaches, and it becomes almost the same. And I've mentioned like how at every iterations you copy the weights and biases. Like you copy the output given by you copy the weights and biases of the first neural network, of the predicted neural network, to the target network, and the target network will give you the output. And you do it for m number of episodes. So like you do some actions, you will die in the game. Then you do some other set of actions, maybe a little better, but again you still die. Then maybe you'll hit the player once and you'll get a then you'll get a headshot, or then such you are improving, and finally you'll reach a position where you are winning the game. You're able to kill everybody. So these are the number of episodes, and it will repeat these number of steps. So the example which I'm going to take is the card poll. In this, if like as Shubham already mentioned, there's a card over here, and there's a poll. So you need to balance the poll on this card. So the information which is given by this environment, like there are 4 kinds of information given. What is the position of the card, the value, and the angle which the pole is at. So various information is given by the environment. And the action which I can take over here is just 2. You can either go left or you can either go right. So 0 corresponds to left, 1 corresponds to right. So you can take go left or right, and your objective is to keep the pole balanced for the longest duration as possible. So we're going to see over here how to implement this. Let me share my screen for the. Can you see the notebook? Can you see this color?
Yeah.
Okay. So in here, you have to install a Pygame module because it's simulating that. Then we have to do pip install. So you have to run it in SMD, of course. You are installing the packages. OpenAI Gym. That is the model which you are using to execute all your algorithms like Q-learning and deep learning. And using PyTorch. So to implement the neural network, you are using that. And here, of course, first you need to create the environment. So the environment over here is card poll environment. And this is the get screen. So it will return the what is the current state at so at every consequent time it will return what is the current state in the game. And it will show the this is just printing the like this is the card environment, this is the card, and this is the pole, and you have to you have to balance that. Then we have the plotting function over here. It is just to plot the values, the episodes and rewards. We are going to see over here. This is a random search. So like I mentioned, probability of epsilon do the random action, and probability of 1 minus epsilon take the this thing optimized action. So initially this strategy is like in here, sorry, over here, random strategy. Initially, it's taking anything. So it's going left, right, or right, left, left, right, any sort of random actions. So this is your goal. Your goal is like 200 over here. This is a value. And this is a score which you're getting. So it's not reaching your goal. And if you see over here as well, scores for last 50 episodes. So last 50 times you run the game, you take random actions. The maximum reward you're getting is 50, but you have to reach 200. So of course, random, you cannot take just random actions. You want the game. So how you're implementing the deep Q learning? There's a class period here. There's a neural network implemented. So torch.neural nm, and it's using the activation functions like array-do linear activation functions. And these are the various functions what's the methods which are being implemented to update the weights of the neural network and to compute the Q values of all the actions. Uh, of course, as I mentioned, environment is the card poll, episodes is the you start the game and then the pole falls down, so that could be one episode. You do some other set of actions. Okay, so you get at this point you're getting that. This is the deep Q learning which is being implemented over here. So it's calculating the reward. It's and it's taking the set of actions. I mentioned probability of epsilon, take the action, random action, probability of 1 minus epsilon, take the argmax. So the best possible, Q value, it will take that action. And every time, at every iteration, it needs to reset the environment so that after one episode, you have to reset it. And that's how it's going to, and it's updating the epsilon. So epsilon is being decreasing by a factor. So the random actions you're doing, which you're going to take, it's going to keep on decreasing. So you're going to take more and more optimized actions. These are the initial parameters which are given. So by DQN, you can see over here the number of episodes which they have took is 150, and to the total reward it's getting is 73. So 200. For one episode, it gave a very good reward like 300, but then it wasn't consistent. It wasn't consistently giving you 200 this things. So that is not what we want. So that is why you're using replay, concept of replay, that is memory. Understanding like keeping it in memory, what sort of actions at particular state, it will give you the highest value. So if you have something in memory, you can use that and it will optimize and it will make your DQN much more better. So that's what is being done over here. There's a memory, there's size limitations and everything. So the initially using the memory, it is giving you like a score of what is it? The score is constantly it's constantly increasing. It's giving you initially it's less because it's taking random actions. Then it's giving you a better. It's giving you higher scores. As you can see over here, this 200. This is your goal, and it's consistent to higher rewards. So again, like if you keep more and more things in your memory, then it will give you much more better reward. So you can see over here, it reached the maximum possible reward it can get. So this environment gives the maximum reward of 500. So it even reached that. So basically, the this thing your what to say, the actions, the model is optimized, and you are ready to play the particle game. So that's it in Q learning and DQN. Do we have any doubts? Do you have any doubts over here? Then check the chat. If you have any doubts, you can put it in the chat. I'll wait for 10-15 seconds. Any doubt in Q learning part or the implementation part or the DQN part? Okay. I'm assuming there is no doubts. All right then. We can end the session over here, right? Jenson?
Yes, Jenson, yes. I said that
Yeah, we'll be sharing a feedback form. Just one moment. Yeah, the feedback form is in the chat. The session recording will be uploaded on YouTube and the code will be available on GitHub. The links are on chat as well. Yeah. All right. If nobody has any doubts, we can end the session.